Today I'll be presenting our work, a deep learning based parametric non-intrusive reduced order model for urban wind flows. Now, the motivation for conducting this work was to take a step towards developing accelerated wind flow model as a digital twin enabler for potential applications in building integrated wind energy or for planning drone operations in urban landscape in a smart city digital twin platform. Now, uh, the regarding the methodology and case study, the case study that we have used is a urban scale simulation involving buildings, and here we want to demonstrate the our non-intrusive reduced order model and its capability in obtaining fields like velocity and turbulent kinetic energy for new values of parameter. And this work, the knowledge gap that we are trying to cover is in the field of we are trying to develop some methodologies which could be used in field of parametric non-intrusive reduced order models. Now, the methodology that we have presenting here, it can be it's said to be comprised of two stages. One is offline stage where we develop the models and it needs the data. So this step can be comprises of three steps, and then an online stage where we use this neuron to generate field for the new value of the parameter. So what's this methodology about? Let's take it stepwise using the case study we have. So in the offline stage, we use the training data from known values of parameter to develop the neuron non-intrusive reduced order model. Now, in the step when the parameter that we have selected here is inlet turbulent viscosity because we want to study turbulent flows. Now we varied this parameter. So we have these four simulations with different values of the inlet turbulent viscosity, and these four simulations helps us to generate a database. These three database, that is for three values of inlet turbulent viscosity, we use it for training, and the fourth value of inlet viscosity, the database, we are using it for testing the model, how good the model is. So we use these three values for training. And in the step 2, as we know, the reduced order models involve decomposing the data into basis functions and associated temporal coefficients. So in the step 2, we use this for each value of the parameter, we obtain the basis functions. Here I'm showing it for the turbulent kinetic energy, but same is done for other fields also. And we can see that the basis functions there I'm showing for three modes. The basis functions reflect the change happening due to the change in value of the parameters. So once we have the basis functions, we obtain the associated temporal coefficients also from POD and POD using snapshot POD method. And then this temporal coefficients, we learn the dynamics of this temporal coefficient in the step 3 using a data-driven model, data-driven deep learning model called as long short-term memory model, which is popularly used to learn the pattern over sequential and time series data sets. So this LSTM helps us to learn the temporal coefficients. Now from the known values of parameter, we know the basis functions and we know the temporal coefficients and the LSTM trained model. Now in the next stage, in the online stage, we use Grassmann interpolation. That is in the online stage for obtaining fields for new values of parameter. That is for new inflow turbulence levels. We obtain new basis functions using Grassmann interpolation. And we use the LSTM model from stage 1 to obtain the associated temporal coefficients with each basis functions. So here we obtain the Grassmann interpolation generated basis functions, and here we obtain the temporal coefficients from the LSTM generated LSTM model. So once we have the basis functions and the temporal coefficients for the new values of parameter, we use it to reconstruct the field. Now we see how the fields are getting reconstructed. For the velocity field, if we see that we are comparing with the full order model. This is full order model. This is our NEROM, and the fields are quite similar. The dynamic evolution is quite similar for a longer time. while in case of turbulent kinetic energy, which is very highly dynamic, we see that as for in an initial flow, the NIROM and full order model are quite similar. But as the flow progresses, some deviation is seen in the values predicted by NIROM and the values by full order model. So here we are comparing the reconstruction of full order model with the our non-intrusive reduced order model methodology for new values of uh, new value parameter. So we also did error analysis, how the error compares. L2 norm is there and L1 norm is also there in the paper. So finally, we can see that the conclude that the parametric NIROM used here involving Grassmann manifold interpolation and deep learning model shows promise while predicting velocity field as well as for short-term turbulent kinetic energy predictions for new values of parameter. And the turbulent kinetic energy fields are showing more dynamics than the other field, and perhaps more tests with larger data set and for different LSTM architecture can help to improve the long-term predictions for TK. So thus this new methodology, as we see here, is showing promise, uh, and it's computationally much more faster and efficient than conducting a full order model simulations, which involves 3D Navier-Stokes equation for the building induced flows. Thank you. Any questions you can, I will be happy to answer.